Hello and welcome to this video on Special Relativity. I'm Mike Malone. Now, I've called this Relativity for Engineers because it's sufficiently detailed to give you a proper and clear understanding of the subject. Your maths does need to be up to basic GCSE level, though I promise you I do keep it as simple as possible with step-by-step explanations as we go. Of course, you can skip the maths bits and go to the bottom lines if you wish, and just trust me that they're correct. The video is in 3 parts, of which this is the first one, and, well, it starts now. The theory of relativity has 2 parts. The first is called the theory of special relativity, and the second, the theory of general relativity. This series of videos covers special relativity only, up to and including the derivation of Einstein's famous equation E=mc². So far, I haven't considered doing anything on general relativity because there is already good material out there which I'd struggle to improve on. In particular, I'd recommend the YouTube channel of a guy who calls himself Dr. Physics A. I'll just put a circle around that there. You can Google that. And his approach worked very well for me. He's a very clever guy. Okay, now to make sure we don't lose track of what we're trying to achieve or where we are in the process, I've prepared this journey route map. Let's skim through it quickly now. So, we start by explaining the oddities that first sparked the whole subject of relativity. Next, I introduce a very simple mathematical process called a transformation, and in particular, one introduced by Dutch physicist Professor Hendrik Lorentz. The next 2 frames are very important. This is where I define what the Lorentz transformation achieves and how it achieves it. So, next we look at 3D space, and in particular how things move between what we call frames of reference in 3-dimensional space, then go on to show how time can be introduced as a 4th dimension, so giving rise to 4-dimensional space-time. Then we ponder how we can express the Lorentz transformation in 4-dimensional space-time, especially since it doesn't look anything like the transformations that move things between frames of reference. In this next frame, this is a very important one. This is where we show that these transformations that looked so unrelated are in fact all exactly the same thing. With this conclusion, we then go on to derive an equation we revealed way back at the start, and this gives us the final piece in a jigsaw that now fits together perfectly. As a result, we give legitimacy to our new 4-dimensional model of the universe. Finally, with all that groundwork done, we take the last big step and derive that equation E=mc². I'll be referring back to this route map at appropriate points so you can see where we are in the bigger picture. So now let's reveal the oddities that sparked this whole relativity thing in the first place. Remember, these are only the phenomenon which special relativity deals with. There are others which are covered by general relativity, which we're not going to touch on here. There are 3 things to consider. They are dilation of distance, dilation of time, and the addition of velocities. All are natural phenomena. Let's reveal them now. Dilation of distance becomes observable when anything moves very fast, by which I mean a speed well on the way to equaling the speed of light. Let's start with a simple question. How do you measure the distance between 2 points, let's call them A and B, as shown here? Well, the obvious way would be to use a ruler, like this. And that shows the distance to be 19 centimeters. What could be simpler than that? Now, at this point we assume the length doesn't vary because it will always measure the same every time we measure it. This is true when things are static, but surprisingly it's not true when we start moving things around very fast. The speed of light can be measured with great accuracy these days, and it's almost exactly 300 million meters per second, which is impressively fast. For the purposes of illustration, I'm going to choose a speed of 2/3 that of the speed of light for a second ruler, so that's 200 million meters per second, and unfortunately that makes it rather difficult to read the scale when the ruler's moving that fast. So what I've actually done is created a snapshot to show you what the ruler would look like if it was travelling at 2/3 the speed of light and had been captured at the instant the zero aligned with point A. Here goes. There. Now, let's see what that distance AB is now, and it looks to me like I'm calling that 14.2 centimeters, plus or minus a millimeter, which is only 3/4 the length we measured with the stationary ruler. This is dilation of distance. The second ruler appears to have stretched when it's moving very fast. So now the distance AB measures fewer centimeters. Now that leaves us in a bit of a quandary, because we know the ruler hasn't actually stretched. That would probably have broken it, certainly if it was a real-life ruler and not a computer animation. However, it's equally silly to suppose that all stationary objects have somehow become squashed up simply because something nearby is travelling very fast. What's actually happened is a relative effect, which can only be perceived when we measure one thing relative to another. Hence, of course, this subject's name, relativity. Now, just when you think things couldn't get any weirder, it's time to reveal the second phenomenon, the dilation of time. To illustrate this, I've attached a stopwatch to each of our two rulers, and I'm going to start them now. I'd like you to try and watch both displays. You should be able to see that the fast-moving ruler's stopwatch is ticking slower than the stationary ruler's stopwatch. Okay, I'm going to stop these after 30 seconds, but you can probably already see that there's quite a few seconds difference. 20 seconds to 15, we're coming up to 25. And we'll stop the stationary ruler stopwatch at 30, 29, 30. There we go. Ah, wow. Only 22 seconds have elapsed on the fast-moving ruler compared with 30 on the stationary ruler. And that is dilation of time. Again, this is a relative effect. You can only see it when you measure the stationary and moving stopwatches relative to one another. So while it's true to say you would age more slowly if you were on a spaceship travelling at such speeds, you wouldn't actually get any benefit from it, because a second would still be the same length of time it always was where you are. Interestingly, the time dilation is the same as the distance dilation for a given relative speed. Stationary seconds are 3/4 as long as moving ones for a speed of 200 million meters per second, the same way that stationary centimeters are 3/4 the length of moving ones at the same speed. I should mention, of course, this is related to the speed of the moving ruler. The foregoing numbers were based on the speed of 2/3 light. If we'd, for example, chosen 0.9 times the speed of light, then our line AB would have only measured approximately 8.3 centimeters. And if we managed to get all the way to light speed, both time and distance would have vanished completely. Yeah, that's what I said. If a photon of light were able to have its own tape measure and stopwatch, they would only ever measure zero. In its own frame of reference, a photon of light is created and destroyed in the same instant and can only ever see itself as an energy transaction between two coincident points. It's only when we observe it from a stationary frame of reference that we see it taking a finite time to cover a finite distance. Okay, you might want to take a moment to think about that. In the meantime, I just want to quickly introduce some shorthand notation, and I have chosen this to agree with that used in most textbooks on the subject. Right, our stationary ruler, I'm going to call that K. and our moving one I'm going to call K dash. Now, a lot of people pronounce that K prime, especially the Americans, so you'll notice that when you look at their videos. I don't know why they call it K prime. I'm going to call it K dash because it has a little dash next to it. The distance will henceforth be x, and the time will be t on ruler K, and they will be x dash and logically t dash on the K dash ruler. We'll shortly be ditching those rulers and instead talking of frames of reference, but K and K dash will keep the same meaning throughout, and you'll quickly get used to using them as part of the language of relativity. Now, let's move on to the final phenomenon associated with the theory of special relativity. This is the addition of velocities. This phenomenon is really a consequence of the first two, but it's important to understand nevertheless. Let me illustrate how this works now with our little red car. This little red car of ours is traveling at a speed, we'll call it v car, and it switches on its headlights. The speed of the beams relative to the car will of course be light speed, and we'll call that v light. Now, in this explanation, do note that all of the velocities are relative to light speed, so let's just make a note of that. And then v light equals 1 here above the car. So, what would be the speed of the headlight beams relative to the road? How would these two velocities add up? You'd be forgiven to thinking that they would just be the sum of the two velocities, but you'd be wrong. Now, it's actually v car plus v light divided by 1 plus v car times v light. And if you care to play with some numbers in there, you'll soon realize that that always equals 1, regardless of the speed of the car. Let's take a look at another example, this time one where two velocities are both less than that of light speed, and see what happens then. So let's choose v1 to be 0.8 times the speed of light, v2 0.9. So the addition of velocities would be, using the same equation, 0.8 plus 0.9 divided by 1 plus 0.8 times v9. And if you care to rattle your calculator, you will get 0.988. As you can now see, this can only ever give an answer less than or equal to 1, and that makes it a very important point to understand. It's easy to be distracted by the notability of light in relativity theory, but it's not actually about light at all. Try to think more in terms of a universal speed limit, because it applies equally to anything and everything, not just light. It's truly a feature of the universe, of the reality we live in. Relativity tells us how it works and provides us with a mathematical model that allows us to understand its consequences, but nobody has ever come close to explaining why it should exist in the first place. Now, remember that equation for adding velocities? We might just be revisiting it later on. In preparation for an explanation of these phenomena, we must first introduce the concept of transformations. Let's start with a diagram showing our two rulers, K dash on top and K on the bottom, like this. And these have stopwatches attached to each one like so. So we're clear, these will be started at the instant the zeros on the two rulers pass one another. That way all the zeros, both time and distance, occur at the same point. Now we're going to start with a low speed, an example speed of only 15 meters per second, so that the relativity effect is negligible and can be ignored. Let's put that in. At 15 meters per second, it's so small your calculator wouldn't even have enough decimal places to show it, so it really is negligible. Just one more thing. We need to know that this distance here is just v times t, where v, of course, is the speed of the ruler k dash, and t is the time on this stopwatch. We're now going to show how to calculate x dash for a given value of x, and it looks like this. So that's x dash equals the value of x for which we're calculating it minus vt, which of course is simply the difference between the two rulers at any time t. As for time, that will simply show that the two stopwatches are synchronized so that t dash equals t at any time. These two equations describe what's called a transformation, because they transform values of x and t into corresponding values of x dash and t dash. This particular one is usually called the Galilean transformation. Now, we know it'll appear to be accurate for a speed as low as 15 meters per second, but if we now increase that to, for example, 2/3 of light speed, 200 million meters per second, this transformation will no longer be correct. So, we now have to find an improved transformation that gives us the correct answer. Okay, a quick look at our journey route map. We've ticked the first two boxes there, by the way. That tells us that the transformation we're looking for is called the Lorentz transformation, and that's named after Dutch physicist Professor Hendrik Lorentz, the guy who first devised it. Let's take a look at it now. As before, here's a sketch of our two rulers. Same notation as previously, and here is the Lorentz transformation. There's the first equation, not looking too dissimilar to the Galilean transformation, where again we're calculating x dash from x minus vt, but then the whole lot is multiplied by this mystery term, and I'll reveal what that is shortly, because I don't want it to distract us just yet. Okay, onto the second equation. Wow, that's looking significantly different to the Galilean transformation. Again, we're calculating t dash, and it equals t as before, but then minus v times x upon c squared, that's the speed of light squared. Finally, as in the first equation, the whole lot is then multiplied by that same mystery factor. Again, I'll not say what that is just yet. In order to understand what's going on here, we first need to state what the transformation's objectives are. Let's do that right now. So the first one, the speed of a single beam of light must measure the same 300 million meters a second against both rulers, regardless what speed ruler k dash is travelling at. Secondly, the transformation must account for the stretching, the dilation that is, of the centimeters and seconds on ruler k dash. Now, let's see how the two equations achieve these, starting with the first objective. Well, the first equation's the same as the Galilean one, neglecting the mystery factor. The second, however, has a new term, vx upon c squared, which subtracts from the time t shown on the stationary stopwatch. When v, the speed of ruler k dash, is just small, this term will be negligible, leaving t dash equal to t, and hence just the Galilean equation. But as v increases to light speed, this factor will increase to the value of t, and hence t dash will approach 0. In other words, the stopwatch on k dash will look like it was started later than the stopwatch on k, and even appear not to have been started at all when v reaches the speed of light. So what does that achieve? Well, put simply, it achieves the first objective of preserving the speed of light. This is very easy to demonstrate. Let's do it now. Let's introduce a stationary torch and turn it on so that the beam of light travels across the top of the two rulers like this. We know that the speed of the beam above k will be light speed. So x upon t will be the light speed c. The question is, will x dash upon t dash also equal c, irrespective of what speed ruler k dash is travelling at? Well, we actually already know it does, so it only remains to demonstrate this. Don't worry, it's very quick and easy. Let's do it now. Now, we know that the speed of light c will be the same anywhere along ruler k, so c equals x upon t, or rearranging that, x equals c times t. Now I also want to allow v, the speed of ruler k dash, to be any fraction of light speed, so I'll define that as c upon a like that, where a is any number greater than or equal to 1. Hence if a equals 2, then v would be a half of light speed. If it were 3, then v would be a third of light speed, etc. You get the idea. So now let's answer that question. Does x dash upon t dash equal c? Let's find out now. So we'll use the terms from the Lorentz transformation in this equation. The first one for x dash. So we'll pop that in there. That's x minus vt. Notice I'm not including the mystery factors in this because they'd cancel out. It's the same top and bottom, and it's actually irrelevant to the first objective of the transformation. Okay, next the one for t dash. So that's t minus vx upon c squared. Now I'm going to manipulate those a bit by replacing the x's with c times t, which I define up here. Let's do that top line first, so that becomes ct minus vt, which I'll just rearrange as c minus v times t. Okay, now the bottom line will replace this x here with ct, like that. And again, we'll rearrange that to give 1 minus v upon c all times t. This gives us the opportunity to cancel t out. That's good. That's a step in the right direction. Now let's replace these two v's with c upon a. So I can now rewrite those as c minus c upon a on top and 1 minus 1 upon a on the bottom. Factorize that top line, so we've got a common factor top and bottom which cancel out and leave us with just c. So that's where we want it to be. We can now conclude that the beam of light has the same speed relative to k dash no matter what speed k dash is moving at. In other words, speed of light is constant. Good, that's the first objective. Now let's go back and look at the second objective of the transformation. This is the one that has to account for the dilation, the stretching of the centimeters and seconds on ruler k dash. It's time now to reveal those mystery terms, these two, and it's the same one in both cases. Let's take a look at them. There they are. Two things to notice. Yeah, it is the same factor top and bottom, and secondly, it's multiplied in both cases, so it's a scaling factor. This adjusts the length of seconds and centimeters on the two scales. So looking at the example we had of v equals 2/3 of light speed, if we pop that into that scaling term, our scaling factor is 1.34. So in other words, very simply, both distance and time are dilated. In this example, by 34%, so centimeters are 34% longer than stationary centimeters, and seconds are 34% longer, or take 34% longer to elapse than those on the stationary stopwatch. So we can conclude that the equations certainly do account for dilation, and more importantly, we can now say that both objectives of the Lorentz transformation have indeed been met. Well, that's it for part 1. It only remains to bring that journey route map up to date, ready for part 2. We've 3 boxes to tick this time. I've introduced the Lorentz transformation, I defined its objectives, and I illustrated how these are achieved. I hope you join me for part 2, where I'll reveal a problem with the Lorentz transformation, the solution to which takes us on a fascinating journey into 4-dimensional space-time. There are also some slick 3D animations, so viewers who prefer to skip the maths can still appreciate what's happening. See you then.